Okay, so after a nice coffee break, we are back for the second session, which is on energy efficiency trends. We are going to listen to 3 presentations by Christoph Böhringer, Marina, Economidou, and Louis-Gaëtan, Giraudet. And Christoph is going to start actually telling us more about energy efficiency and the role of general equilibrium effects. In the rebound literature, very often you find the differences on direct rebounds, spending rebound, and economy-wide rebound. So he's going to focus on the last part, which is not partial equilibrium, but general equilibrium, and is going to show us how this can be detected and used in policy analysis. So, Christoph.
Yeah, so thanks a lot for the introduction. Thanks also to the organizer for having me here. It's always a pleasure to come to beautiful Barcelona. This is joint work I did with a colleague from Ottawa, Nick Rivers. And the background, I think, is fairly well known. So from a policy perspective, energy efficiency is sometimes hoped to be a central instrument or path to reduce greenhouse gas emissions, to put it in more climate policy context. But economists are a little bit more skeptical on that, and not only we here in the room, but it goes back to 1850 to Jevons, who basically had this seminal economic insight that as something gets cheaper, which basically means energy efficiency improvements, it will be used more. And so the idea here is actually to provide a more rigorous taxonomy of what is an energy efficiency rebound. I will come to that with 2 or 3 slides. And then to assess the different channels for energy efficiency rebound in a more rigorous manner. So the issue being, okay, we start from an energy efficiency improvement, what we would call an energy efficiency improvement from an engineering perspective. For driving our car or heating our house, we need 1% less of energy. How much energy savings do we have? The energy savings from an energy perspective would be nothing. There's no economic response. So everything being the same, ceteris paribus, we have a 1% energy savings, but with economic responses at different levels that I will discuss, that might fire back, and you will not achieve the full 1%, or you could also say 100%, depending on what is the basis of your shock. So Andreas already indicated that there are different notions of the rebound effect. So typically what is well investigated is what I would call the partial equilibrium rebound. And that's the rebound that comes from a change in the energy price or energy service itself. So we think about electricity as an input becoming 1% cheaper, everything being the same otherwise, and then we assess how this translates into energy savings. That would be what I call the partial equilibrium rebound. But then, in a broader perspective, there are interactions, with your heating or electricity demanding activity and other activities. And as I will show, that can go as far as saying, well, there is an investment effect, capital channel effect, there is a labor leisure choice effect, because at some point also energy will affect the real wage, and then given that you have a labor supply being elastic, that has also some effect. Okay, so that's basically the setup. We have also within both categories, but now sticking to a partial equilibrium, you could basically differentiate. I do that at the end here of a tree between the direct and the indirect rebound. So the direct rebound would just measure, the electricity savings per se, but not if this electricity, say, is associated with steel demand. So you basically need less electricity, you produce less power, you produce less power plants, and then the steel also has some embodied energy which you could count to be an indirect effect. So this would be called the full embodied energy savings if we take the direct and indirect effect together. What you also see here is, I call it substitution and income, which would refer to the classical micro-Slutsky decomposition. So usually what you see in the literature in terms of a rebound effect is, a combination out of the demand effect or substitution effect and an income effect. And so as a rule of thumb, if you have an energy demand elasticity of 50% and an income elasticity of 10%, then the rebound effect would be 60%. So for 1 gigajoule that you save initially in engineering terms, you would basically forgo 60%, 0.6, and you would only have a net saving of 0.4. What we are doing now in our paper is a more rigorous theoretical exposition with an analytical model on the different channels. So we embed in a channel equilibrium setting with a free sector model, and you can read the specifics in the paper. We basically can decompose analytically, with tree in the different effects, and I will also tell you in a second what type of general equilibrium effects we consider, because general equilibrium could be still partial. If we look at the broad economy effect for Spain, but we keep international prices fixed, you could call that a general equilibrium effect, but you would forgo about the feedback effects from international fuel markets, for example. So I will be more specific on what we talk about with 4 key channels of general equilibrium rebound. And then we take the analytical model, which is fairly simple. We can use just a few parametric values, say the energy share of a economy like Spain or the US, some key elasticities, and do a back-on-the-envelope calculation on what is the rebound effect, part partial and part general equilibrium. And then we transpose the same thing in a more complex numerical model, computable general equilibrium model, and we test how the order of magnitude changes, the ranking, and we find that the partial equilibrium stylized representation pretty much comes close to what we get in a general equilibrium setting. So let me now tell about what we talk on the general equilibrium channel. So you see here 4 channels that we consider. One would be the composition effect. So imagine we have different sectors. We talked about that with the ETS or non-ETS. Some of these sectors might be more energy intensive than the average and the other one less. And so the composition effect, for example, would contribute to the rebound, meaning increase the rebound if the sector who is getting more energy efficient, say the energy intensive sector, then is more energy demanding with respect to the output than the rest of the economy, okay? Because then you make this sector attracting resources from a less energy demanding segment of the economy, and that basically will increase the rebound effect. It's just a very standard composition substitution effect across different activities. The energy price channel that we mentioned here, as you will see in the numerical calculations, has a pretty important role. So you may be familiar with carbon leakage, and this is the same mechanism which we could call energy efficiency leakage, as to reduce energy demand, now here through energy efficiency improvements, but it could also be through a carbon tax. You drive down the demand at the international level for fossil fuels, and to the extent that the fossil fuel supply is elastic or inelastic in this case, you drive down international fuel prices, you make international fuel cheaper, and that might give a energy price channel rebound. And then there's the Krav Effect. So you can show in our stylized model that by means of higher energy efficiency, you increase capital productivity, and therefore you have in a steady state model, steady state closure model, you basically have an increase in savings investment, and with a higher capital stock, you come to more output and more energy consumption. And last but not least, which will not play a big role in our model, but we just included it, is the labor supply channel, which I already pointed out, the basic mechanism. So I only have one little slide to illustrate how the analytics go. The model that we have is fairly stylized. We linearize the model, and then we can provide closed form solutions. So in the model, we can add with different channels by saying, we make labor being elastic or not. We include a investment response or not. We include multiple sectors or not. And we develop everything from a single sector model towards a free sector model where we have X, Y as being two production sectors that use value added and energy services, and then we have an energy sector that basically also uses a fixed resource to give a certain convexity to the supply and therefore have the energy channel in there. And you see with the R, that's the notation for the rebound. So if we have 1% energy efficiency improvement on the left-hand side, you see two terms on the right-hand side that are dropping out very standardly from analysis that many folks did before. So it's the substitution channel and the income channel, and with the parameters in the income channel is alpha, it would be the energy intensity. So that basically is the income effect, which is typically very, very small. So energy intensity of the US is 3%. So if you take that as one-to-one into the income rebound effect, that's simply 3% out of 100% where you would have a rebound. And the substitution channel that you see on the first term is the substitution sigma X, is the substitution in X production between the value added and the energy service. And then the theta Sx is the value share of energy service in X production. And if you take this product, it's nothing else than the compensated energy demand elasticity. So, this is fairly straightforward, nothing new. And now, step by step, we add more complexity in the analytical model. For example, the last equation here illustrates this composition channel. The first parameter is something which goes from the analytics, is a reduced form representation of a more complex functional relationships. But what is important here is the sigma u and the parentheses. So the sigma u is the elasticity in final consumption. U stands now for utility, where we trade off X and Y, the two goods in our stylized economy that can be consumed. So this is the cross-price elasticity of substitution between, say, a more energy-intensive and a less energy-intensive sector. And then what you have in the bracket is the alpha E again, that's the average energy intensity. And then the theta is basically the energy intensity of the Y production, which could be more energy intensive or less energy intensive than the average of the economy. So here we think about the X sector receiving an energy efficiency push, an autonomous one, and what will happen then through the composition channel is if the other sector, which is the Y sector here, is more energy efficient, then the theta YS will actually exceed alpha E, and then we get a negative rebound. It's the other way around, we get the positive rebound. Okay? And if the two sectors are identical, the bracket just cancels out to be 0, and then there is no composition channel rebound. Okay, so I've given the time constraints. I already come to some results. So what you see here is we use data from the US Bureau of Economic Analysis 2010 in order to parametricize this stylized model with key numbers, for example, energy intensity. And then we also take some elasticities where the empirical evidence is not so clear, is it short run, mid run, long run. So what you see on the left-hand side is the sensitivity of the rebound effect across these different channels with respect to a change in the sigma X. Okay? And the sigma X was the substitution elasticity in the X sector between energy services and the value added. And in the experiment, we basically say this X sector gets a push in terms of cheaper energy. Energy services become 1% cheaper. And when you see the black line is actually the partial equilibrium rebound, that would be the sum out of the substitution effect in a more narrow sense and the income effect. So it's the own price elasticity plus the income elasticity of energy demand here. And then we can go further. So you see that, if we take the red line, it doesn't really change a lot. So the composition channel at an elasticity of substitution of sigma u, which we by default parameterize at 0.5, so a CS function, is not kicking in a lot. Then we add the labor supply channel, which is the blue line, and then what you see here are two variations on the energy supply elasticity, and the higher the energy supply elasticity, the lower is the rebound effect, because the downwards drop with a given energy demand is not that accentuated, right? So you see with a low energy elasticity of 0.5, you get the blue line, and that actually adds substantially to the initial partial equilibrium effect. You see, as we make the sigma x, which is basically governing the energy demand elasticity, if we approach 1, then the partial equilibrium effect dominates more and more and more, which is, not surprising, but it basically also indicates that if people come up with low energy demand elasticity and say, well, the rebound effect doesn't matter because the energy demand elasticity is small, then, the general equilibrium effect could actually dominate. So it's an elasticity, say, of 0.2. The composite of the other channels that I mentioned can be higher than the 0.2, the 20% loss that we get from an energy demand elasticity response. And on the right-hand side, you see then a similar sensitivity analysis with respect to the elasticity of substitution in final consumption. I still have a time constraint in mind. We have 2 more, to be time efficient, we have 2 more slides. I think that's okay. So I presented with stylized results, and now here you have results in a broader applied equilibrium model. So it's a macroeconomic model calibrated to empirical data. In our case, it's 2014 base here using the GTAP database. And we do this illustrative shock for different economies, China, EU, US, and then we do it also for different sectors. So one bar here, if we start with China on the very left, for agriculture, we say energy demand becomes cheaper for agriculture. What are the components of a rebound? And then you see that roughly across these colors and boxes, the energy rebound, the partial one, goes along 50%, and the general equilibrium components go at a third of it, like 16 or 70%. So the total general equilibrium, including the partial now, rebound could go up to 67% or 2/3. And pending, as I said, on the parameters that you pick on elasticities, mainly value shares, then you get a share of a general equilibrium which could be 16% out of 67. So that's a ballpark figure. Interestingly, the numerical results line up quite well. So you could also say, what the heck do we need this big general equilibrium model? But in the bigger general equilibrium model, of course, we account for much more complex substitution possibilities than in the stylized analytical model. Okay, so I come to the conclusion. So I think the contribution of the paper that we now try to sell to a decent journal for a year already, or half a year, is, there are, of course, it's always, people say, well, there's a lot of work already done, so what's the value added? And now the conclusion tries to make our point for value added. So we think there is still a lot of confusion about the terminology, what is the rebound? So we develop a more concise, not a unique, but a more concise tautology, a terminology on the, not tautology, a terminology on the different components of the rebound, and then we decompose that in an analytical model in a rigorous way, and then we do this theory with numbers, I call it, where we use both an analytical model and a large-scale simulation numerical model to assess how important these different channels are. And I think the main conclusion is that if the partial equilibrium rebound seems to be small, so the hopes of policymakers saying, well, energy efficiency improvements can save the world, should be taken with care, because the general equilibrium component can really kick in. If a partial equilibrium rebound is pretty high, then general equilibrium doesn't matter as much. And within the components of a general equilibrium, the international fuel price channel plays the most prominent role. Thanks for your attention.
Thanks a lot, Christoph. I would propose that we first have all the presentation and then hopefully 15 minutes for discussion. We can combine them, the different perspectives. So I would then move to the second speaker, Marina Economidou, which is going to show us an index decomposition approach on energy efficiency improvements, looking at different drivers of these changes, and as well illustrating this for European countries. So the floor is yours.
Thank you very much, and good morning, everyone. It's a pleasure to be here today. Thank you for giving me this opportunity, not only because I get the chance to share the results of my work, but also it's a great opportunity to listen to all these really interesting presentations and discussions, and I see that the agenda will remain very engaging until the end. So my name is Marina Economidou. I work for the Joint Research Center of the European Commission. And unlike what my surname may suggest, I'm not an economist, I'm an engineer by background. But I did this work together with Rocio Roman Colato, who is a professor of economics at the University of Seville, who is not able to be here today and sends her apologies for that. And today's presentation is on the assessment of energy efficiency trends in the EU productive sectors. And we did this analysis by deploying monetary-based and physical-based index decomposition analysis. Just a couple of words about the GRC, the Joint Research Center of the European Commission, for those who don't know us. We are the science and knowledge service of the European Commission. So we have this fortunate position to be the research institute inside the EU's executive arm, and we participate therefore in policy-making discussions. And we really work at the interface between science and policy. And therefore our mission is to support EU policies with independent evidence-based research throughout the whole policy cycle. We have sites in 5 European countries. I'm personally based in Ispra in Italy, and there is another site here in Spain, in Seville, that do more work on economic analysis. And we have a number of different laboratories, so we do more scientific research, but also more work related directly to policy, so we provide a lot of direct policy support related to policies that deal with EU citizens as a whole. So you can imagine we work on a variety of different topics. Now, what is the trigger of this work that I'm presenting here today? As you know, the EU has set a number of targets as part of its energy and climate package. And one of these is the energy efficiency target for 2020 that has now been extended to 2030. But in terms of 2020, we see that overall from the diagram here, we have done considerable progress towards these targets, with 2014 being the year where we observed the lowest energy consumption. However, since then the consumption has been growing. So in the past 3 years, 2015 to 2017, and also the very latest data from 2018, which came out a couple of days ago, confirm this trend. And therefore, it's an alarming trend that we need to investigate further. And this is the reason exactly why we do this kind of analysis, because we need to provide more evidence to policymakers as to what are the reasons why energy consumption is increasing or is decreasing, and what are the key trends that come out of that. So we've been using index decomposition analysis to study energy efficiency and to look at the energy consumption trends in various sectors of the economy at member state level and at EU level, and try to understand why the trends are going on the way that they are. Today's presentation and the focus of this paper is on the productive sectors of the economy, so that is the industry, services, and agriculture. We also cover residential transport sector, but that's a different paper. And those three sectors together are responsible for around 42% of the total EU share of the final energy consumption, and also 13 trillion euros of gross value added. And we see that over the study period, which was from 2000 to 2017, we have had in these sectors an overall reduction of 5% at the EU level, but at the same time an increase in gross value added of nearly 30%. We deployed a twofold approach to study the energy consumption changes in these sectors. We used logarithmic mean divisor index method to decompose aggregated energy consumption changes into activity, structural, and intensity effects. And we use this method because it carries a lot of advantages, such as no residual, it's consistent in aggregation, the fact that you can consider multiple effects, and etc. And we also use activity revaluation approach in order to assess these sectors and be able to assess them through a physical-based approach. That means that we are able to look at intensity from a physical perspective rather than a monetary perspective, and therefore able to remove the price effects. And we have done this analysis only for the industry sector because that's what the data allows us to do that. So what effects have we considered? We consider activity effect, as I mentioned, and this we actually divided into employment and labor productivity, where employment measures economic activity in terms of labor force, and that's in terms of hours, total hours employed. Labor productivity, which reflects changes in productivity due to, for instance, advancements in equipment used in production processes or penetration of technologies enhancing output per unit hour worked. We also investigated structural effects in order to look at whether shifts in the composition of the sectors from more energy intensive to less energy intensive, and vice versa, have had any impacts on the energy consumption changes. And lastly, obviously, intensity effects, which we use as our main proxy for energy efficiency. And we have done the same analysis with the activity evaluation method in order to do this assessment now using physical units, and specifically industrial physical index, in order to remove the price effects. And here is an overview of the factorization identities that we considered. So for the productive sectors, we decompose the energy consumption changes for industry, services, and agriculture as a whole at member state level and then at the EU level together, using information about the employment, the labor productivity, structural changes, and intensity. We have done the same analysis for industry, where we looked at 11 subcategories within the industry sector, which allowed us to look at more the structural effects in more detail. And lastly, we did this assessment to compare how results differ if we use a monetary approach versus a physical approach, using for the first gross value added and for the second the industry production index, and that was done for industry sector, and we were able to do this decomposition analysis for two industrial sectors, manufacture and construction. Moving on to, results, too fast. Okay, so we see here the changes in the EU energy consumption, final energy consumption of the productive sectors overall over the period of 2000-2017, where in total we had a reduction of energy consumption of around 26 million tons of oil equivalent, which is equivalent to around 5% of a reduction. And we see that the activity effect has had a major driving force in energy consumption, both in terms of employment and in terms of labor productivity. However, these were more than offset by gains in intensity and also by changes in structural, in the structure of these sectors overall. And this is mainly due to the fact that we move more. The services sector has become more important over this period of time, and services being a less energy-intensive sector would result in a pattern like this that we see here. The same sectors, all productive sectors, together over a period of time. So here we see the yearly results. We see that basically there are two distinct periods from 2000 to 2008. That's the first one where the main inhibiting forces to energy consumption were exerted by the structural and the intensity effects, but these were only partially offset by the positive activity and the positive activity effects. And these positive activity effects favored an increase both in employment but also in labor productivity, because we see that these two effects are positive. Then in the second part, from 2008 to 2016, we see that the important negative change in final energy consumption was explained not only by the structural and the intensity effects, but also by the employment effect, which has been negative, and this is linked to the economic recession that we had in 2008 to 2009. So this was accompanied by lower employment rate, although the efforts to improve energy efficiency, we see from here that continued to be important even in that period. Then in terms of the industry sector, we were able to see that, in fact, for the industry, the employment effect was negative, so it drove down energy consumption over the period from 2000 to 2017, while labor productivity increased. And at the same time, by considering all the different subcategories within the industry, we also seen a shift towards less energy-intense sectors within the industry sector, but nevertheless, intensity has been the main contributor towards this overall reduction we've had over this period of time. Now, some results regarding the comparison between physical units and monetary units based on the industry production index and the gross value added. We see here that the general trends remain the same. However, when we take into account, when we evaluate intensity in terms of physical units, then the results are a bit more modest, so, as you can see from this diagram here. So, yes, as I said, we see the general trends to remain as before, with intensity being the main inhibitor over this period of time, which is good news. However, what an interesting result we get is that the structural effect take into account only these two sectors, because we're able to decompose energy consumption based on this analysis only for two sectors of the industry sector is positive rather than negative, which highlights the need to look at a more detailed sector analysis. And nevertheless, the negative IPI-based intensity effect seems to be of lower magnitude, which means that in general that the gross value added based analysis may overestimate the intensity improvements that we see from this kind of analysis. So as some conclusions from this work, we can see that energy consumption is still coupled with economic activity, and that we can see that from the yearly results that we've seen for the productive sectors, and I showed you before. We also see that the structural effect is conditioned by the level of disaggregation within each sector individually, and that was the case for the industry sector. So it's important to carry this kind of analysis also for other sectors. We also have seen evidence for the digitalization of the productive sectors as a whole due to the negative structural effects that we have seen. But nevertheless, energy intensity remained as the main inhibitor, both in terms of physical units, but also in terms of, obviously, in terms of monetary-based units. But as a future activity, we'd like to include finer levels of disaggregation in our analysis in order to be able to conduct a more detailed decomposition and get more detailed results as to how these sectors are changing over the years and how energy efficiency contributes towards reducing energy consumptions. And that's it. Thank you very much for your attention.
Okay. Thanks a lot, Marina, for this presentation. We will surely discuss as well afterwards, in the Q&A session. But now I would move to Louis on the last presentation, which is on differentiated green loans. So you're looking at consumer prices and look at price differences for home retrofits, automotive, and so on, looking at potential inefficiencies that are associated and detected in analyzing this data. So
yeah, thank you. Thank you, Andreas. This is joint work with Anna Petronevich and Laurent Faucheux. And well, I'll be very quick on the motivation. We all know how important home energy retrofits are to cut CO2 emissions. And the bottom line here is that home energy retrofits involve substantial upfront costs. A serious retrofit would be in the 10,000 euros or more in the 15 or even higher. And so obviously, if for such big amounts, most of the time you need financing. So the bottom line is that if we want home retrofits to deliver, it is important that credit markets function well. And so we are addressing this question. So some basic intuition on loan pricing. Obviously, loan prices should reflect risk, okay? And so if you start with this reasoning and you apply it to different project characteristics, then you would expect the following. So if there is an energy efficiency component to your investment, then it should reduce your energy use and hence your energy bill. So this will either make you more credit-worthy or increase the value of your property. So anyway, it lowers the risk. And therefore, you should expect the interest rate to be lower than for an otherwise conventional investment. And then if you look at other characteristics of your retrofit, of your investment, so the characteristic not related to energy efficiency, then they should not particularly lead to a different interest rate, especially if you compare a retrofit to an automobile. Both provide services, And if you ignore the collateral issue, which we would discuss, but it's relevant to our empirical analysis, you should not expect different interest rates. So you expect the following ranking: no difference between retrofits and automobiles, but when they are green, meaning energy efficient, you expect a lower interest rate. And we will simply test whether this is the case. So actually, this is a very little studied issue, and to our knowledge, there's only one study that looks at how interest rates vary with the designation of the loan, and this is especially Anne and Pivot, who study commercial mortgages in the US, and they find that buildings that were certified green at loan origination have a better loan terms. Okay? And there is another paper, but it looks at default rates, which is a slightly different focus from ours. So this last result that I showed suggests some sort of efficient pricing of energy efficiency. But first, there is a selection issue. They don't control for borrower characteristics. And there is one source of variation only. They compare green to non-green loans, but they don't explore other characteristics of the asset. And they focus on new constructions, which from an emission point of view are less important than renovations or retrofits. So against this background, what we do is we study loan rates, but we look at two sources of variation, whether it's green or non-green, and other characteristics of the asset. And we look at unsecured consumer credit, so which is different from mortgages. And the key aspect is that we use a novel data set of posted interest rate, and I'll be more specific about it in a minute. And so we circumvent this selection issue that I mentioned before. So using posted interest rates are pros and cons, which I will detail in a minute. So with this, we find actually counterintuitive results in the sense that we find worse terms for retrofits than for automobiles, and even worse terms for green versus conventional retrofit. So it's the interaction between the two results that's important. And results are robust over a range of specification, but they vary over time. I will show you that. So what we do, basically, we scrapped data from a bank website. So if you go to this bank website, all banks in France offer online simulators. So you enter an amount you want to borrow, a duration you want to borrow over, and then you can select a different loan designation among a menu offered by the bank. And then the simulator returns you an interest rate and a total cost of the loan. Okay? So, and interestingly, they don't query anything about income or credit score. So what comes out is a pure pricing of the bank in relation to like only the amount you want to borrow, the maturity of the loan, and the type of asset you want to purchase. Okay? So we scraped data from 15 French banks every week over 2 years. And for every, we did all the possible combinations of maturity, category, and amount every week. So in total, we retrieved over 240,000 observations, and we base our analysis on this. Okay? So obviously, these are posted interest rate, not the rate that you effectively contract if you take a loan. So you might be concerned that it doesn't reflect the true the market interest rates. So here we compare our posted interest rate in blue diamonds to actual rates for consumer credit as made available by the Banque de France. And you see that if anything, we're a little above, like by 0.3 percentage point, but the two follow similar trends. So we're not so far off from the data. And the fact that we are a little above suggests that there might be some negotiation between the bank and the loan applicant, and that leads to slightly lower interest rates. Okay, so then, obviously, all banks have different simulators, and they don't offer the same menu of assets, okay? So we have to build categories to compare assets across banks. Okay, so we have to interpret the type of assets that they offer. And we are specifically interested in 3 categorizations. So categorization 1 is whether the good is just a conventional good, or whether it has a green characteristic, like whether it's energy efficient. Then we are interested in vehicles versus retrofit versus other loans. And then in a third categorization, we interact the 2 characteristics. So vehicle green and non-green, retrofits green and non-green, and others. So it's important to mention that only one bank makes a difference between green and conventional autos, and only 4 banks make a distinction between green and conventional retrofits. But most of them make a distinction between vehicles and renovations. So I'll skip the time series. And then we apply the simplest econometric model you can think of. We regress the spread on the loan against loan characteristics, which are essentially the amount borrowed and the maturity of the loan, a project dummy that reflects our categorization, and then bank fixed effects and bank and time fixed effect to take into account the conjuncture. And we test the 2 hypotheses that I mentioned earlier, whether the coefficient for a green asset is lower than for a conventional one, and whether it's the same for retrofits and automobiles. And here is what we find. So in the first column, we only look at whether an asset is green or non-green. And here we find that the green characteristic leads to slightly lower interest rate, but it's not significant. Then when we compare vehicles and retrofits, we find that interest rates are actually lower for vehicles than for retrofits. And when we interact the 2 characteristics in the third categorization, we find that actually green cars lead to lower interest rates than conventional cars, but for retrofits, it's the opposite. Like green retrofits carry higher interest rate, are offered higher interest rates than conventional retrofits. Okay, so then we look at year subsamples, and we see that when we look at the green characteristic in 2015, being green was a penalty. It led to higher interest rate, where it was the opposite in 2016. So things seem to improve on this respect. And there was also a twist between 2015 and 2016. Like in 2015, a retrofit was cheaper than a car, and then it was the opposite. Okay? And when we interact the 2 dimensions in the subcolumn, it's consistent with these separate effects. Then we replace our fixed effects by macro and financial factors, just to give a better intuition as to what drives the conjecture. And interestingly, the only variable that pops up as significant is unemployment, and with a negative effect, meaning that when there's more unemployment, interest rates tend to be lower. So this is important for what I'm going to say toward the end. And then we conduct placebo tests, because there is one concern, obviously. As I told you, we have to interpret the loan designations, and especially whether an asset is green or non-green. So if I go back, so obviously it's easy for cars, because there's only one bank that offers green cars and that labels it like that. But for efficient renovation, as you can see, We retain those measures that mostly affect the thermal performance of the building. So we group certain measures together. And you might argue that, okay, there is some arbitrariness in this categorization. So we do some robustness check. We conduct placebo tests, which means that we take all designations and we randomly allocate them to 2 categories, as if there was a green and non-green categories, but they were randomly allocated to it. And in a statistical test, we fail to reject that the coefficients are the same, meaning that there's no difference in the estimates when we randomly allocate them, whereas in other tests, we find that when we build our categorization, we reject the hypothesis that the coefficients are the same. And in a third robustness check, placebo test, we reject the fact that the random coefficients are equal to those that we estimate on the true categorization. So this means that our categorizations are relevant. So to conclude, regarding our first hypothesis, whether interest rates are lower for energy efficiency than for conventional investment, we find that this is the case for automobiles, but it's only driven by one bank. And it's not the case for home energy retrofits. And whether interest rates are the same for retrofits or automobiles, holding all borrower characteristic constant, we find that it is not the case, where as you would expect it to be the case. And automobiles are overall cheaper. So it could be that if you look at home energy retrofit, they suffer from a double energy efficiency gap, so they are priced at very high rates. First, because they are retrofits, and second, because they are energy retrofits. Okay. So I will close with some candidate explanation as to these results, because this is mainly a descriptive analysis. So why the green aspect seems to be rejected? I mean, it less the case toward the end of the period, but at the beginning it seemed to be the case. There's a literature that says that it's hard to trust energy savings, and realized energy savings under-delivered compared to predicted energy savings. So if this is the case, that might be internalized by lenders. And then perhaps more interestingly, why is it that retrofits and automobiles are not priced the same? So you might think that there are different subsidy programs for these, but actually there are subsidy programs for both. So tax credits for retrofits, but also fee-based for cars, and so they are of a similar order of magnitude. So it's probably not very important. And so our conjecture is that lenders use the project designation as a screening device of the wealth of the borrower. And we think the most reasonable conjecture that a lender could make is that a household that wants to borrow for retrofit is most likely a homeowner, and hence is wealthier than the average borrower for an automobile, who can be anyone. And since homeowners tend to be wealthier than the average population, this is a conjecture that they would make. So if risk management was a primary effect, then you would expect that if the borrower is wealthier, then the interest rate is lower. But then a loan is also like a standard good, so it can be priced also as a standard good. And if this is the case, then if there is price discrimination, you would expect the price to be higher if the buyer is expected to be wealthier. And it seems like this effect dominates in our finding, and the fact that we find that unemployment has a depressing effect on the interest rate lends support to this hypothesis. But for sure, it deserves more work. That's it. Thank you.